Meanwhile, I introduce the next speaker. The next speaker is Fei Miao, who is an assistant professor in the Department of Computer Science and Engineering, and also a courtesy faculty at the Department of Electrical and Computer Engineering at the University of Connecticut. Something about Fei: she received her Bachelor of Science degree in automation from Shanjiao Tong University, and she then got her PhD together with a master in statistics from the University of Pennsylvania, for which she won the best doctoral dissertation. She was then for a while a postdoctoral researcher at GRASP Lab. So her research interests lie in the optimization, machine learning, controlling in theory, and essentially she applies these tools to address safety, efficiency, and security challenges for cyber-physical systems. Today in her talk, she's going to talk about learning and control for safety, efficiency, and security of cyber-physical systems. And I'm a big fan of her work, so I'm very excited about hearing more in this talk. And therefore, I give you the stage, Fei. Go ahead. Yes, you're muted.
Okay, thank you for the introduction.
And I don't see yet the full screen mode.
Not full screen mode.
Like I see, it's not in presentation mode.
It's not in presentation. Also, it's currently. So is it? So it's the presenter mode. Okay, so let me.
I actually see the slides on the left. The slide deck on the left.
Yeah, let me change. Let me reshare the.
Sure, no problem. We are being very good with time, so
yep.
There's no stress.
Let me just share desktop and see. Yeah. Can you currently see
yes.
the? Okay, great. Okay.
Yes.
Yeah. Thank you for your introduction and thank you for inviting me for this workshop. Today I'm going to mainly talk about our group's work about learning and control for safety, efficiency, and security of cyber-physical systems. So the science of CPS emphasizes the tight integration of communication, computation systems with the control of physical dynamic systems. And it's just proceeding. Okay. Yeah. So today I'm mainly going to talk about our work on transportation systems and connected autonomous vehicles, mobility on demand systems in this line of CPS work. So the first topic, we would like to introduce our work on data-driven robust optimization for mobility autonomous on-demand systems. Well, the challenges we'll focus here is nowadays we are collecting increasing amount of data in smart cities. Meanwhile, it's a challenge, say, usually these systems are large scale, and even we have data and we can utilize machine learning tools to extract model knowledge based on data, still, we cannot guarantee, say, the model is 100% accurate, and we have to consider what's the effect of model uncertainties in the following decision-making process. And today, we would like to introduce how we first analyze model uncertainties based on learning methodologies, and then in the optimization and decision-making procedure, how we consider these model uncertainties while improving the fairness and efficiency of the service of the entire system. So the first challenge we would like to focus is the current unbalanced and inefficient smart city service like mobility on-demand service. So the algorithms have been developed for these years, but still we can see scenarios like places with high demand only has low supply, or places with not that much demand may have idle taxis or idle vehicles that drivers just traverse on streets and looking for their next passengers. And this sort of scenarios getting worse with the rapid expansion of EV, that it is economic and environmental benefit, but meanwhile, the control algorithm side also has more challenges in the sense that EV needs to be regularly charged, and the charging time is difficult to predict, and charging stations may also have the imbalance in the sense that places with low spots may have a long waiting queue of drivers waiting for charge, and some spots might not be fully utilized. So the challenges here we consider is, okay, now we can collect both historical and real-time sensing data to reflect the vehicle status and to reflect the charging station status. And how can we start from these data to predict the future passengers' mobility demand and also EV supply while considering this sort of model uncertainties, and in the algorithm design side, provide a better balancing algorithm to improve the efficiency of the entire system. So first, we start from the algorithm of construct a prediction uncertainty sets from data. So the methodology is usually we partition the entire city to some regions, and within each region we can using aggregated data to represent like the total number of trips start from these regions as demand, and the total number of, for example, idle vehicles within the region as the supply at a different time of one day, and this is a dynamic process. So traditional techniques like time series analysis provide nice prediction of these models. And nowadays there are STM neural network and transformer neural network that also predict the time series data. But in our methodology, instead of just using the prediction, the estimation of these model, we assume that the real demand or the real supply is the prediction plus some residual. Basically, the error we assume we can construct a model of these error set based on data. So the methodology is we using bootstrap process, repeated sampling basically, to construct the confidence region of the estimated mean and the covariance of the prediction residual through the training process, and build finally a closed convex set that related to these mean and covariance. Or simply we can just build a range, say, okay, with 1 minus epsilon probability, the total number of mobility demand or the total number of EV supplies within specific time and specific region of one day can be within this range, instead of only using like a deterministic value to represent the prediction. And for the uncertainty set construction algorithm part, we proved that the parameters are guaranteed to be contained in certain confidence region with the desired probability. So then on the vehicle balancing algorithm side, we can do this dynamic balancing process in the sense that at every time step t, like every 30 minutes or every hour, we first collect the current status of all vehicles. Is this vehicle empty, or it has a passenger on it? Does it have enough battery or not, etc. And then fill in this prediction to the uncertainty set model and build the uncertainty set model for the current time step t. And then on the optimization algorithm side, so we will later mainly talk about this part. This is all the major contributions. Say we design a system level vehicle balancing algorithm that provide fair and efficient service with minimum balancing cost for the entire system. And after this sort of centralized vehicle balancing decision has been made, it will be sent to vehicles and also like local controllers to do like a vehicle to passenger assignment, or vehicle to our carpool routing process, etc. So our main contribution and focus of this talk will be on the system level algorithm design. So for EVs that providing mobility on demand service, basically our prediction will include mainly two parts: the predicted demand, which is assumed to be satisfy some probability distribution, and also the predicted available charging spots for EVs that needs charge, also assumed to satisfy probability distribution. Instead of saying, okay, we know the exact probability distribution from data, we're saying, okay, we actually build an uncertainty set that contains the possible probability distribution. And on the decision-making part, we mainly balance EVs that needs charging to available charging spots. And we also balance EVs that with enough battery and empty, means without any passengers on it, to potential locations that with unsatisfied demand in the future. Basically, we also balance empty vacant EVs to serve passengers in the future. So the decision part includes two parts. Basically, one part is about serving the mobility demand, and another part is about satisfying the EV's charging requirement. So the optimization problem in a high-level definition is looking like this. Basically, it's a min-max problem, as we want to minimize the balancing cost under the like a worst case probability distributions of the predicted demand and the EV supply. And the optimization problem objective function part includes both the balancing cost and the fair charging service requirement. And the fair mobility service means the supply-demand ratio at different regions of the city should be close to each other, means that basically passengers at different locations can receive a similar level of service by the AMOD systems. The major novelty of this problem formulation is it is the first to consider both the demand and the supply side uncertainties for autonomous mobility on demand system. And also this problem formulation decoupled the mutual dependency between the EV supply and mobility demand, in the sense that basically the EV supply will be mainly affected by this fair charging process. Say after these EVs finish charging, they will turn to new supplies in the system. And the mobility demand requirement, say providing fair mobility service, is placed in the constraint part. And with this problem formulation, basically we can prove that this problem formulation with decision variable on the denominator and uncertain parameter on the numerator, it satisfies the requirements that this problem formulation is concave of the uncertain parameters and convex of the decision variables. Though it's not a linear or quadratic format of optimization problem in the literature, but since it has the nice property of concave over the uncertain parameter, we can prove that this min-max problem has an equivalent format of convex optimization problem. So we can solve the problem and provide a real-time vehicle balancing solution for AMOD systems. And in experiments, we compared the performance of our algorithm in several cities. And here we mainly show the comparing result in Shenzhen city's data, that we show that with our distributed robust optimization algorithm solution, we can reduce the average vehicle balancing cost, and also we can reduce the variance of the cost around like different times of experiments. Basically reduce the variance for the cost means we improve the robustness of this algorithm under like a different prediction, demand and supply prediction errors. And for example, in improving efficiency side, the average, the total driving distance, total idle driving distance is reduced by about 14%. That means like EVs, there is already like the mileage anxiety, right? So if a lot of mileage is cost by searching passengers without any passengers on it, then that's not an efficient operation. So with our method, we can reduce the total idle mileage, basically that improve the system's efficiency. And we also compare the service fairness of our methodology, and we show that The unfairness is measured by like the supply-demand ratio of the charging service and the supply-demand ratio of the mobility between like the passengers' mobility demand and the available EV supply. So the unfairness on both charging and mobility service part is reduced by our algorithm. It means that by considering the vehicle balancing in both serving passenger side and the charging requirement side, we again improve the fairness of the system, that vehicles need charging receive relatively similar charging time, and passengers who need mobility also receive relatively similar service. So also by our experiments here, we basically shows like fairness and efficiency. These are like a correlated parameters or correlated factors we should consider for the system, that if we co-design in one optimization problem, then both metrics can be improved. Along this line, and we recently submitted a work to this year's ICRA that since reinforcement learning-based approach, a multi-agent reinforcement learning-based approach has the advantage of, say, it does not require as many model knowledge as optimization or model-based approaches. So can it improve the system performance? But instead of just using existing multi-agent reinforcement learning algorithm, here we design what we call a robust constrained MARL algorithm. The motivation is with a lot of advantages. The reinforcement learning methodology always has a criticize, say there is a simulation to reality gap. So if the policy is not trained with like the data well aligned, or a simulator well aligned to the real world, then the policy we get can really collapse or can have a performance degradation in the real world. So to address this issue, we have to consider, say, in the training part, we need to consider model uncertainties in our simulator, and to consider, say, the simulation to reality gap is through the training stage. And our methodology is, okay, compared with the literature definition of MARL problem, we don't assume the state transition probability is some fixed probability function. Instead, we assume there is a transition kernel that represents the uncertainty set for the state transition probability. And all the state action reward definitions are as the literature. And under this problem formulation, we design a robust constrained MARL algorithm to provide a solution, basically train a robust policy through the training stage and compare our methodology, the performance in terms of system fairness and total rebalancing cost or idle mileage, and also the order response rate, expired order rate, etc. These sort of factors with existing optimization-based method and also existing reinforcement learning, but not robust method. And we show the improvement of our system's performance. And you can check the detail on arXiv. Okay, so this is the first part of my talk about mobility on demand system. If there is no questions, I will just start the second topic of today's presentation, which is also the recent focus of our group. Starting from about 2020, that we have been working on safe and efficient multi-agent reinforcement learning for network CPS, and especially connected and autonomous vehicles. So we would like to understand that how we can better utilize the shared information among connected autonomous vehicles to improve the behavior planning, to improve the reinforcement learning performance and the control algorithm design for the entire system, and to provide a safety guarantee and efficiency improvement of the entire system. Hence, we can formally quantify and validate the benefits of communication on improving connected autonomous vehicle systems, safety, and efficiency. So the first step, we consider the CV system model as a hybrid system model that the decision the vehicles need to make, for example, include discrete space as the vehicles need to select whether I should keep lane or change left or change right, for example, on a highway driving scenario. And meanwhile, the lower level controller needs to compute like what is the specific control input in the continuous variable space, say like the steering angle or throttle I need to input to the system to execute the decisions. And the challenges here is if it's just a single agent, then the current reinforcement learning algorithm may work well. But in a connected autonomous vehicle system, we also need to consider, okay, this can be a very large scale system. And if we just use like the existing actor critic algorithm for multi-agent reinforcement learning and has a very large scale centralized queue function to train, that may not be practical for the real world system. And also consider the communication capability. It's really hard for one agent to really get the global state and action. And meanwhile, the traditional reinforcement learning does not really have a hard constraint on the safety of the actions taken, though it can have penalty for unsafe actions, but the trained policy later cannot really guarantee safety if we don't add additional model knowledge or additional requirements to the reinforcement learning process. So in this work, we consider to utilize the shared state and action information from other agents where the communication capability of CVs. And then we design MAR algorithm to do the behavior planning part and to improve the system's safety and efficiency. So in MAR literature, there have been different algorithms to do the policy training and like actor critic algorithm, or Q learning algorithm, etc. And recently, people who work on physical dynamic systems have been designing these safe reinforcement learning algorithms, but most of these algorithms are for single agent reinforcement learning, that it does not specifically consider the coordination or communication among multi-agents, or if it's multi-agent algorithms, it actually interrupts the learning process with some safety shield. And in our algorithm instead, we actually want to integrate the part of control dynamic knowledge and what we call safety action mapping process to the learning process of MARL, in the sense that the safety mapping part will basically project unsafe actions to safe action space checked by a CBF control barrier function-based QP controller, that this part of state and action experience will be saved and used to train the MAR process. So the structure of the algorithm is shown as in this figure, that it's a safe actor critic algorithm. Basically, the CBF QP controller part provides safety action mapping, and this part will be utilized in the policy training process. And this is how we solve the safety challenge that in our paper, we have details to show how we prove the safety guarantee with this framework design. And meanwhile, instead of just using a centralized critic or centralized Q learning method, here we proved that every agent can only focus on its local, like 3 to 5 neighboring agents' state and actions, and utilize these shared part of information to do its own Q function, through both the learning and training process. And we showed that what we call this truncated queue function, instead of using the global state, global action, we only use localized neighboring agent states and actions to utilize this information sharing. And we can prove that this truncated queue function, the error of approximating the global queue function is bounded. And here we want to mainly show some results of our methodology, that when there is different human-driven vehicle percentage on streets, using our safe MAR algorithm, we can always improve the average velocity and average comfort of all these autonomous vehicles on streets. And meanwhile, we also compare our algorithms with the baselines without a safety action mapping, that we always get a higher episode reward in both training and in the testing procedure, since without a safety guarantee, those cars are hard to keep like a relatively good distance between its leading vehicles. So it's hard for the reinforcement learning algorithm to really learn to keep this safety distance in a very short like training time in, for example, 20 episodes. But if we add safety guarantees as like a safe action mapping, these RO methods also trains faster, that it quickly learns to keep a safety distance. And also here we have a short video showing the experimental result that basically with our safe action mapping algorithms, all these vehicles run smoothly on streets, and without the safe action mapping, sometimes those vehicles get confused and they cannot really coordinate with the neighbors very well. And one interesting scenario especially is what we call obstacle on the corner scenario, that there will be a traffic jam formed without shared vision when here there is a black car has accident and suddenly parked there. So other vehicles don't know what happened before they get closer to this corner. So it's easily a traffic jam just formed here. But if there is shared state information among connected autonomous vehicles, before the cars really approaching the corner, they get the information from the leading vehicle saying, okay, on this left lane, the average velocity is very slow. So these cars learn to change to the right lane even before it really see what happened at the corner. And along this line, recently, we also have a new we also have some new design for more challenging scenarios. Say, okay, if the autonomous vehicles can face some really like aggressive drivers, and for example, this red car, even at the red line, this red car is running, so basically violated the traffic rule. And for the CVs, it can be a very challenging scenario if in the training procedure, it doesn't consider this sort of dangerous or hazard vehicles. And we designed a new safety shield and active critic algorithm to coordinate these CVs that basically the methodology is every CV cares about its own safety, say without collision with surrounding vehicles. But meanwhile, they also want to coordinate that all vehicles successfully pass the dangerous vehicle, the hazard vehicle, instead of, okay, one vehicle passed, but the following the other vehicles still failed to avoid the collision. And we show the comparing, basically, we show with safety shield, even in like the very hard hazard conditions, the successful rate can improve just significantly. And without safety shield, it's kind of no hope for these CVs to avoid the obstacle, even they have communicate with each other. And I might not really have much time left, but I just want to mention our work about reward reallocation for motivating cooperation in ML. So in the literature, people usually just assume these agents will coordinate. Instead of saying, okay, what is a good reward allocation scheme to motivate them to coordinate? If they coordinate, can every single agent also get higher reward instead of only the system get a higher reward? And the main idea here is we revise the reward function design in the sense that in the literature, usually reward is only a function of state and action. But here, our reward is also a function of the correlation. Correlation means the groups of agents coordinating in this scenario. And we define what is called a Shapley value-based reward allocation scheme in the sense that every agent will get some additional parts of reward from the entire system according to its marginal contribution or its proportion of contribution to the entire system's reward. And we have proved that this reward allocation scheme is efficient in the sense that the entire system's reward is allocated to every single agent. And we also proved that this Shapley value-based reward allocation scheme is stable, means that actually with this reward allocation, every agent already gets the best payoff it can receive by coordinating, and that they will just stay within the correlation, communicate with the other agents and cooperate. And again, we show the reward improvement of the entire system by this Shapley value-based reward allocation scheme in connected autonomous vehicles examples. And I think I will just skip my part of work of security, but the high level idea here is for cyber physical systems, the cyber attack can also cause disaster on the physical dynamic part, like autonomous vehicles or connected autonomous vehicles. But we also have additional knowledge from the physical dynamic system that we can utilize to design a resilient control algorithm, to design resilient coordination framework for the entire system. And I think in the future, our group will also work along this line. So finally, I would like to thank you for my PhD students and also some undergrad and high school scholars. So most of the work I present today is collaborating with all these students. And if you want to know more about our work, you can check our website, and a lot of paper also has their individual website and video showing the work. Thank you. I think I will just stop here for questions.
Thank you very much, Fei, for the great talk. Let's open the stage for questions. We have some time. I'm looking at the document for the audience to put questions, and since nobody has questions, so I'll ask a couple, and then I'll also invite the other speakers. Maybe they have questions. My question was related to the first part. So first of all, I really like that you do both sides of the game, right? You look at the more mobility thing, but also the vehicle level things. This is great. Regarding the first part, I think we were already discussing about this, but this connects to work that also Marco in the past did. Actually, Marco now left, but it's work that they did on this, I think LSTM, they did it with the LSTM. Can you talk a bit about the comparison of the two performances that you get?
Yeah, so I think the main difference is Marco's work. I remember I read their papers. There are like model predictive control based methodologies and PC based methodology, and there are like a queuing theory based methodologies. And I think I would say the big difference here is our group focusing on how to address the model uncertainties in decision making. So we do not, so we don't restrict the demand prediction parts algorithm. So it can be LSTM, it can be just a time series, or it can be, say, assuming this passenger arrival rate follow Poisson distribution, for example. So we don't restrict this mobility demand parts assumption. Instead, say, okay, so no matter what's the original prediction on the demand part, we mainly focus on what is a prediction error, and through the data training procedure, we focus on construct an uncertainty set for the prediction error part, and then say, okay, in the following optimization based decision making part, how we address these like a model uncertainties in the optimization based approach. And we have been so today I mainly talk about this like a min-max of expected cost. This is what is distribution and robust optimization, and we have also papers about like a robust optimization based approach. And we basically comparing, say, okay, if we want to also improve the robustness of the algorithm, what can be the performance? So of course, and improving robustness sometimes can result to like a conservative performance of the algorithm compared with, say, not considering any robustness issue. So just utilize the deterministic value of the prediction part, right? So if the prediction result is very good, then using the deterministic value of the prediction definitely will benefit the decision-making part. But if the prediction result is not that accurate, or maybe we just start this algorithm on some new city, we don't have a very large data set of historical data yet, even they use state-of-the-art prediction algorithm, it does not provide like a very high accuracy algorithm, right? So under those scenarios, considering model uncertainties will have benefit. So the main benefit is when the prediction is not that good, and using this robust optimization algorithm, so the performance, say like idle driving mileage or service fairness, will be improved compared with like using deterministic value as the mobility demand or supply. Yeah.
Thank you very much for the great explanation. There is a second question actually from Kara Kokelman, and it connects to something I also wanted to ask. The question is, I wonder how difficult it is to get those dynamic visualizations you showed. This is referring to the second part of your talk. Can you comment more on the kind of software that you are using? Is it open source? Are you thinking about sharing it for other researchers to be used?
Sure. Yes. So first, this software part, it is open source. So it is called Color. So I think it's maintained by some non-profit group. So everybody can access it easily. But I have to say that when we first started this simulation, there are like some obstacles of using it. So for example, it is like playing some video games, so we can use, for example, the keyboard to control the move of these vehicles, right? But if we really want to simulate a good interaction of autonomous vehicles with different types of human driving behaviors, so those parts we need to do something. So for example, when they want to simulate some like some hazard vehicles violate traffic rules or accelerate or decelerate suddenly, this sort of behavior, we need to like write code, manually code it, and then to control this, for example, hazard red vehicles behavior. And also using it to simulate a reinforcement learning process, say it doesn't have issue to, for example, it doesn't have issue to implement our like decision of changing lane or keeping lane, but we do need to do something to connect this with reinforcement learning, the backbone training process. And also, especially the difficulty happens when they want to implement like a CBF-based controller or even PID-based controller on the software, because first we need to find out the system identification, the dynamic function, for example, bicycle model, those parameters in this system, and that does need some time. And needs some like a trial and tune the parameters and the algorithms, etc. So I would say, so there's seems the gap mainly exists from like the integrating the reinforcement learning, multi-agent reinforcement learning part with the control of the dynamic part, and to find out that which way we could utilize the strength of both of these two algorithms in both the framework design and also in this simulator, because naturally it's not designed for like integrating all these parts together, and we have to figure it out by ourselves. Currently all these things I think we have the paper online, we have the videos online, and our students are like cleaning the code part and to publish like how they implementing these things in the color environment. Yeah, so the color itself is open source software, but like how to really successfully run these reinforcement learning with CBF-based safety shield experiments, those parts are not open source yet and are not really that easy to implement. But I think our students are cleaning the code, and we will publish it online soon. Yeah.
Thank you very much, Fei. That's great work, and we are perfectly on time to go to the next speaker. So I thank you again
I will stop
very
sharing.
much.